Hi again, everybody, and welcome back. We're continuing Chapter 11 on uniform circular motion. And so far we've done horizontal uniform circular motion, which is fine. But now with vertical uniform circular motion, there's a little bit of a difference, because if you go in a vertical circle, you've got gravity acting with you on one side of that circle, and you've got gravity working against you on the other side of that circle. Think about going in a loop on a roller coaster, all right? At the bottom of the loop, you feel perfectly fine in your seat. At the top of the loop, you hope you stay glued to your seat, because you could have the possibility of falling out because of gravity. So there is a lot of similarities, but there is one or two differences as well with vertical. First of all, with vertical uniform circular motion problems, always draw a free body diagram. Usually you're going to draw this object going in a circle at the bottom and also at the top, sometimes even on the sides as well. But always draw a free body diagram so that you can label the forces that are in the radial direction towards the center of the circle. All right, what kind of forces might they be? There might be tension. Like, for example, let's say you're swinging a bucket of water around vertically. Right, well, there's tension in your arm because you're keeping that bucket in a circle. Could possibly be the normal force. Now, the normal force, now this is kind of interesting. The normal force here acts as your apparent weight. Like, for example, you're standing here, okay, and you have your weight force, mg, okay. Well, the normal force is really, we've called it your apparent weight before. Remember how we talked about in, I believe it was chapter 3 or 4, how if you're going in an elevator up or down, if your whole system is accelerating, the normal force, that is the force that the floor is applying to you, may be different depending on if you're going up or down. You still have the same mass, and the gravity is still the same, but your apparent weight, also known as normal force, will change depending on how much the floor is actually supporting you. So this is going to be kind of the supporting force, or the apparent weight, or you might say the weight that you feel at a certain point around this vertical circle. And also gravity as well. Like I said before, gravity works different directions depending on where you are in a vertical circle. Secondly, always write the net force. I usually write net force C for centripetal is equal to the mass times the centripetal acceleration. All right, this is like Newton's second law right here, just kind of modified for circular forces. Then, of course, you always write your net centripetal force as a function of all the various component forces that are creating it. Force 1, minus force 2, plus force 3, etc. One thing you want to keep in mind also is that with a circle, towards the inside is positive, towards the outside is negative. That's also one thing to keep in mind as well, because some forces are going to act towards the center, others are going to act towards the outside. In many cases, you'll need to solve for some sort of minimum or maximum value, but in most cases, what you're going to do is just set your equations equal to that value. So that'll be the minimum or maximum speed, or the minimum or maximum velocity that you must be going at in order to stay in a vertical loop. Like, for example, if you're spinning a bucket of water around, okay, so you're holding that bucket right there, and you may have noticed, if you've done this before, that as you spin it around, the water can stay inside the bucket as long as you spin it around with enough velocity. Okay, the water won't fall out. But the question is, what is that velocity? What is the minimum velocity? You can certainly go over that velocity, but if you go under it, you might be in trouble. All right, so there's a couple things to think about when doing this kind of problem. So let's go ahead and give an example problem a try. This is example 11, you know what, it should be 11.9. Well, I'm not sure. We had messed up our numbering system before. This might be 11.11 actually. I'll change that. I think it should be number 11. But regardless, it is the example that has the guy riding the motorcycle inside the loop of death. We'll call it that. All right. So example 11. Let's take a look at this and see if we can make some sense of it. So we have a guy at a circus, right, riding this motorcycle inside this enclosed loop right here. All right, where is he most at danger? Up here, right? Why is that? Well, because gravity. Oops, that is too fat of a line. Gravity is acting towards the center of the circle, and he could potentially fall. All right, so we want to kind of adjust. We want to solve for, especially this right here, how fast does it need to be going to stay in contact with the track. All right, so we've got the radius of this track being 5 meters. Okay, we've got the mass of the motorcycle right here. And we need to find the minimum speed or the minimum velocity for V such that the motorcycle wheels maintain contact with the track. All right, so where are the wheels going to have the least contact with the track? Well, probably at the top, right? In fact, at the top, if he's just barely touching the track, the wheels are touching, but it isn't really creating any force between the track and the wheels, then we can say that the normal force, I'll do that in blue, the normal force equals 0 newtons. There is no pressure between the wheels and the track. They're just barely touching, but there's no additional pressure. So they just barely maintain contact with the track, so he can actually stay on top and not fall into the middle. Okay? Down at the bottom right here, in fact, I'll call that N sub C, is 0 newtons. So if he were riding over a bathroom scale right here, it would register virtually nothing because he's just barely touching it. Down at the bottom, it's going to be different. He's going to appear to weigh more or feel like he weighs more. Here will be different as well. So we're going to solve for the required velocity of him going around the track for C. Why? Well, because C is the most dangerous part right there. He'll certainly stay on the track here and here if he's going a certain speed, but right here we need to solve for that. So what I'm going to do is I'm going to shrink this down a little bit. Like so. All right, so at C. This is the part A, okay? At C, what are the forces that are acting on the motorcyclist? All right, well, what is the net force acting on the motorcyclist? Net force at C. Net force centripetal at C. There's 2 C's there. All right, well, there is a normal force, which equals 0, right? There's just barely no normal force. But what else? What other forces acting on the rider there at C? Well, there's weight force, of course, right? That's mg, the mass of the rider and the motorcycle. Okay, that is the force that is threatening to pull him into the middle of the circle and have him fall down to the bottom and break his neck or something like that. Okay, so we have our 0 Newton normal force plus, remember that's directed towards the center, so is mg, plus mg. Just like that, okay? So these are our component forces. No normal force, but mg. Okay, how else can we state the net centripetal force at C? And how can we state that a different way? I say this all the time. We can always state it as being what? Newton's second law, right? M times the centripetal acceleration. All right? So, these two statements being equal, we can set them equal to each other. So, m times centripetal acceleration equals mg. Okay? Now remember, we're solving for the velocity. How fast does he need to be moving such that the centripetal acceleration is equal to his weight right there? Well, that's locked up in our AC right there, right? So let's just kind of describe that in more detail. So mass times, how can we write centripetal acceleration with regards to velocity? I think we can do it with v squared over r, right? Equals mg. Good, let's solve for velocity and see what we get. Okay, so we're going to bring the r up Oh, actually, what can we do with the masses right there? Masses on both sides, we can cancel them out, right? So whatever velocity this is, this would apply for pretty much any mass. Doesn't matter how massive the rider or the bike is, it would apply for any mass. So let's solve for V. Make sure I get the right color here. I'll get blue. So the V is going to be, see, I'll multiply the R up and then take the square root. So that is the square root of RG. All right, so R is 5 meters, and G is 9.81 meters per second squared. So our required velocity, you might say, or your minimum required velocity, is the square root of all that stuff. So 5 times 9.81, take the square root of that, 7, essentially 7 meters per second. All right? And don't let this min or max scare you. Just think about it like this. If he goes any slower than this, what will happen? Well, his wheels will come off the track up here. He won't be able to maintain contact with the track, and he'll probably fall to the inside of the track right there. If he's going faster than that, then great. All the more pressure between the wheels and the track, but he has to be going at least, at the bare minimum, that speed in order to maintain contact with the track. Okay, so let's now find, so this is part B right here, we want to find the normal force exerted on the motorcycle at parts A, B, and C. Well, we did C already, right? Because at C, we said if he's going at this required speed, 7 meters per second, his wheels are just barely maintaining contact with the track, which means it's just barely touching it, which means there's no pressure between the wheels and the track. So therefore, there would be no apparent weight or no normal force. So at C, the normal force at C, and this is what we assumed when we first solved for the velocity, is going to be 0 newtons. The question is, what is the normal force at B and the normal force at A? All right, that's what we want to find out. So let's look at B right here. All right, the normal force, in fact, I'm going to kind of that's kind of messy. I won't do that. The normal, I'm just going to draw it small like this. The normal force is going to be directed towards the center like that, because that is normal, or you might say at right angles to the surface that he's riding on. That's what normal means. Okay, call that normal at B right there. All right, so at B, the net force directed centripetally is the normal force, right? The normal force. Is his weight directed centripetally? Is his mg, is that directed towards the center? No, it's directed this way, right? It's at right angles to that, so that's mg right there. That is neither contributing nor hurting his normal force, but it's at right angles to it, so it's not going to be part of the center directed forces. We can just ignore that. So the normal force at B would be the only force, the only component force directed centripetally right there. All right? Well, what's the other way? How did that turn red? What's the other way that we can state the net centripetal force at B? I should put a little b right there. Well, that's mass times centripetal acceleration. All right? These two things being equal, we can say then that the normal force at B equals mass times centripetal acceleration. So the mass of the bike and the rider, I think, is 350 kilograms times the centripetal acceleration. Well, we didn't calculate that out, but we know how to find that. That's v squared over r, right? So the velocity is 7 meters per second. I'm just going to leave the units out. Squared over the radius, which is 5 meters. Okay, so the normal force at B equals what? What do we get? I get 3,430 newtons. And so if he were riding over a scale right there at B, that's how much it would register. All right, because you have to have some strength of this, you might say the stiffness of the round wall or the round loop, providing enough force to keep him inside the circle, because that's the only thing that's doing that. All right, how about at A? I think we can squeeze this all in one right here. At A, and in fact, let me do that in a different color because that way you can tell it apart. I'll do that in, I'll do that in purple. Why not? At A, right here, what do we have going on? Well, at A, we have, where is the weight force directed? Straight down, right there, right? mg. What direction is the normal force directed in? It's directed upwards. Normal at A, right there. So these now are competing with each other. So not only does the normal force have to counteract mg, but it also needs to provide enough force to keep the rider in the loop to provide the centripetal acceleration. So we can say that at A, then the component, the component forces at A, centripetal forces, are the normal force at A minus mg. Why did I not put mg minus the normal force? Well, because remember, towards the center is positive, towards the outside is negative. So the NA is going to be positive, that's going to be negative. Okay? What's also true? The net centripetal force at A equals mass times centripetal acceleration. All right? So we should know how to find that. Let's put those all equal to each other. NA minus mg equals mass times centripetal acceleration. All right, and so we're going to have to add over our mg right here in order to get NA all by itself. So our normal force at A equals mac plus mg. All right, I'm really running out of space here. What's our, actually, let's tell you what, let's do this. Let's maybe make it a little bit simpler. Equals mass times AC plus G, right? I just factored out the M right there, so it might make it easier to calculate. So the normal force at A is going to be, what's our mass? That's 350 kilograms, right? Times centripetal acceleration. Oh, I wish we'd actually calculated that out. Well, that's all right. We have it at 7 squared over 5, right? That's the velocity like that right there, and there's our radius. That's our centripetal acceleration. Plus g, well, we know that it's 9.81 meters per second squared. Okay, there we go. Now we can actually solve for our normal force today, and we'll actually explain why it is like this. All right, 350 times the quantity. Let's see, 7 squared over 5 plus 9.81. And I get 6,863, or 64 we'll go with, newtons. All right, look at that. Compare that to this right here. The normal force would be at A, that is, the supporting force at A, or the apparent weight at A. He weighs twice as, or he feels like he weighs twice as much at A as he does here. He weighs nothing right there. So as he goes around, the way that he feels, his weight keeps changing, and that should make sense because when you come down a hill in a roller coaster and then you come back up, all right, that track right there has to supply a lot of force to not just keep you from going out of the loop, but also to balance out your weight. So you really feel heavy right here. And as you go up, you feel less and less and less heavy, and then you feel not very heavy at all. And then you go around like that. So you weigh twice as much at the bottom. You weigh what you would probably normally weigh at rest on the side, and you weigh just about nothing at the top right there. So that's a kind of a common application of centripetal forces, uniform circular motion in vertical directions. So I hope that made sense. Thanks for following along. See you on the next one.